VSEPR theory is the simplest approach to thinking about shapes of molecules. And you probably were exposed to this in your prerequisite class. VSEPR, that's not technically how you'd say it, but that's the closest we can get to being able to pronounce that. Valence, shell, electron, pair, repulsion theory. And the idea here is that electron groups around the central atom repel each other. So here we have an illustration of a molecule. There's a central atom and three other atoms that are bonded to it. There's a pair of electrons in each of these single bonds. Each pair of electrons is considered a group. And this group repels that group, which repels this group, which repels that group. And they're trying to get away from each other. And so the idea is that you look at the number of electron groups and you look at how they're going to arrange themselves in three-dimensional space around that central atom, and that helps us to predict the shape of the molecule. So the electron group can be a lone pair, a single bond, or a multiple bond, or if you have a radical, it can be a single electron. And we're looking at repulsions between electron groups on interior atoms. We don't care what lone pairs are on this terminal atom. That doesn't affect the shape at all. We're just looking at atoms that are in the interior of the molecule. And the preferred geometry is going to have maximum separation of electron groups. That's going to give the minimum energy. It'll be most stable. Draw the Lewis structure for beryllium chloride. Okay. I write those things to myself because otherwise I forget what I'm supposed to do. So beryllium chloride, we're going to put beryllium in the middle and chlorine over here and chlorine over here. And how many valence electrons do we have to mess around with? 16? Yeah. So we'll make a bond here that's 2, 4, 6, 8, 10, 12, 14, 16. We ran out of electrons. What should we do? Should we make multiple bonds? Some things violate the octet rule, right? Is beryllium one of those atoms? It is. It's one of those little guys that violates the octet rule. So this is actually the correct Lewis structure for beryllium chloride. If we look at formal charges and compare that with making some double bonds or something, we'll find out that this is actually better. So this is the Lewis structure. To find the geometry of this molecule, we're going to look at the central atom and identify how many electron groups are around the central atom. Well, there's a single bond here and a single bond here. That's two groups of electrons. How can two groups get away from each other? They can be on opposite sides of the central atom. I think of this a little bit as like the central atom here is the Earth, and here is you, and here's your X. And you really hate your X because of what they did to you. And so you're going to be over here if they're over there. You're going to be as far away as possible, right? That's going to make you the happiest. So these electron groups hate each other as well. I talk a lot about things being happy. This is about hating. I can't remember where I was. I shut the door, shut out the train.
Oh, hatred.
Hatred. I was on hatred. Thank you. So, we mostly talk about happy, but now we're talking about hating, getting away from each other. So these groups are going to be on opposite sides of the central atom. Maximum separation, 180 degrees. And so if the bond is here, then the atom it's bonded to is at the end of it. And so we end up with all three atoms in a line. And so this is a linear geometry. The geometry is linear. If we look at CO2, let's see if I can squeeze it in here. Not that way, I can't. If we look at the Lewis structure for CO2, we're going to end up with this. And looking at the carbon in the middle, how many groups of electrons are there? there's two groups. This double bond has 4 electrons in it. But those 4 electrons are shared between the carbon and the oxygen. They can't get away from each other, right? So we count that as one group. And this double bond, those electrons are stuck between the carbon and the oxygen. They can't spread out, so it's one group. So it's not number of electrons, it's not pairs of electrons, it's groups of electrons. So 2 groups, they'll be on opposite sides. It also has a linear geometry. Any questions? What about 3 groups? BF3, boron trifluoride. You know, if I told myself to draw all these structures, I should have left myself a little bit of space. You know what? I'm not going to use blue. I'm going to use orange. Because then I can write over the blue line and still see what I'm doing. So boron, oh, that's this. There's boron, trifluoride, and we're going to have octets around the fluorine. We're going to find out that we would run out of electrons to give boron an octet. Is boron going to be okay with that? Probably, because boron is a little guy, and he can be satisfied with 6. So when we look at this Lewis structure, we look at the central atom, and we have 1, 2, 3 electron groups. So now there's 3 things getting away from each other. This isn't 180 degrees now. They're going to spread out at a 120-degree angle, and that's also known as a triangle. Right? There's a triangle. It's an equilateral triangle, if you care. So that's a trigonal planar geometry. It's a triangle and it's flat. It's in a plane. All the atoms are flat. The angle there is 120. And angle we're looking right here. The angle between those 2 bonds is the angle we're looking at. If we look at formaldehyde, here's the Lewis structure for formaldehyde. It also has 3 groups. 2 single bonds and the double bond. Again, the double bond is one group. And so that's also going to spread out in a 2-dimensional triangle, trigonal planar. The angles here are not exactly the same. 121.9, 121.9, and 116.2. And what that tells us is that this oxygen is a little more repulsive to the hydrogens than the hydrogens are to each other. They're like, man, we really hate oxygen. I don't like you either, but I'm willing to get a smidge closer to you so I can get farther away from him. So what these atoms are affects the angles, but it's roughly 120 degrees. 4 groups. Now this is where things get harder to visualize. And I should have brought balloons, but alas, I did not. If we think of the balloons, if we tie 2 balloons together, they will push each other away, right? That's that linear geometry. If we tie 3 balloons together, they'll form a triangle, but they'll be flat. And remember, these balloons are representing electron groups, not atoms. If we stick a 4th balloon in there, what's going to happen is it's going to push these guys down a little bit. And we're going to end up with 109.5 degree angles between all of the balloons. And this forms a tetrahedron. A cube has 6 sides that are squares. A tetrahedron has 4 sides that are triangles. So this is a tetrahedron. It's a triangular prism. There's a triangle at the bottom and it rises to a point. These angles are 109.5. And this is how 4 things can get away from each other in 3-dimensional space. It's called a tetrahedral geometry. And this is a really important one to be able to visualize. So methane. If we look at the structure for methane, Lewis structure would be like this. There's no lone pairs anywhere. We look at carbon. It has 4 single bonds to hydrogen. There are 4 groups. 4 groups form a tetrahedron. 109.5 degrees for their bond angles. When we look at the Lewis structure, it looks like it's flat, right, and making a square. But what would this angle be? That would be 90, right? And here's another 90. So the hydrogens are closer if you squash it down 2-dimensional. If you allow it to pop up and be 3-dimensional, the angles are larger. These 4 groups are trying to get away from each other. So this is better. Any questions? What about 5 groups? Here's phosphorus pentachloride. There's one that violates the octet rule. 5 groups. 5 groups form what we call trigonal bipyramidal geometry. And I envision this as being a little like a girl. So here's her hair, right? And she's a ballet dancer, and this is her tutu. Okay, and she's spinning. Okay. No, she doesn't have 3 arms. And she doesn't have one up in the air. It's her skirt, her tutu. Okay, I'll get rid of that. But we have 2 of these that are opposite to each other, and the other 3 are going to form a trigonal planar around the middle. This is the best they can do. The angles are not all the same, but that's because you can't take a 3-dimensional sphere and divide it equally into 5 pieces like this. It just doesn't work. So there's 90-degree angles between this top one and the tutu, and between the parts of the tutu is 120 degrees. Because these are different, we call this the axial atom, and these are equatorial, because they're like the equator. And these are along the axis. This would be the North Pole and the South Pole, and these guys are around the equator. With balloons, it'll look like this. And you can try that at home. The tricky part, of course, is tying the balloons together. I've snapped lots of balloons in class. And this is the 3-dimensional representation. So that's what 5 groups do.
So these are the valence electrons.
We're not looking at the valence electrons. We are looking at the number of electron groups on the central atom. So this central atom has 5 single bonds. That's what we're looking at. The lone pairs on these chlorines have nothing to do with it. Very good point. 6 groups. Sulfur hexafluoride, 6 single bonds. So now we still have the straight up and down, but now we've added 1 atom to the skirt, to the equatorial position. When we do that, now we've got 90-degree angles between everything. And so this does not have an axial and an equatorial. They're all the same. This is an octahedron. Octahedron. There it is in balloons. And here it's drawn out. 90-degree angles. You need to know these shapes. You need to be able to look at a Lewis structure and tell me what shape the electron groups are going to make. And the way you do this is, how can they get away from each other? Well, 2 is going to be opposite, and 3 makes a triangle. You can memorize the table, but that's no fun. Question?
What is the importance of the angle?
The importance of the angle. The angle can be measured and gives us evidence of which structure it has. Yeah, I can't think of a great reason that we're talking about the angle right off the top of my head, but I know there's a good reason for it. Yeah. Definitely with this one, the angles are significant because we'll find that the bigger ones, the bigger ones are going to go around the sides, And the smaller ones will be on the top and the bottom because they take up less space, and so they can handle the smaller angle. So there definitely are implications for the angles themselves.
Is there a reason they use octa as the prefix for the 6 electron groups?
Yes, there is. The reason is it has 8 points. I'm sorry, it has 8 sides, not 8 points. So on the top, there's 1, 2, 3, 4. On that side, 1, 2, 3, 4. There's 4 sides, so it's an octahedron. Good question. Let's look at this. Determine the molecular geometry of carbon tetrachloride. First thing to do, Lewis structure. So we're going to put the carbon in the middle and put the chlorines around it. That was a little too curvy. How many valence electrons do we have to deal with here? We got 4 from the carbon, and there's 4 chlorines, and they each have how many valence electrons? 7. So 32. So I've already got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. No double bonds on this one. We draw the Lewis structure. We look at the central atom. How many electron groups? 4. 4 electron groups. So that means its shape is what? Tetrahedral. Yeah, tetrahedron has 4 triangular sides. An octahedron has 8 triangular sides. And you can't do it with 5. It just doesn't work. Any questions?